Hi there, welcome to the final session on the topic of vectors for the Year 1 portion of this course. So we're going to be wrapping up what we've done so far, and we're going to also have a look at a few more examples in terms of modelling with vectors, how this can be applied to, for example, amongst other things, mechanics problems, for example, force, mass, acceleration, and velocity, distance and time. So vectors are going to come up quite regularly in the mechanics side of the course as well as the pure, so they are very crucial in terms of understanding how things work. So before that, of course, we do have some warm-up questions as ever. So here they are. I'd like you to, as ever, attempt these on your own without me helping you, and once you've tried them to the best of your ability, press play on the video and see how you've done. But for now, press pause, stop it, try these in a quiet space, do your best, and then only play the video to see how you've done and to check if you've got them correct, and if not, to make those necessary corrections. Okay, so if you're ready, let's have a look together at question number 1. So question 1, this is GCSE really, but it's always worth remembering. So we've got a bearing here, so we need to find the bearing of B from A. So for B from A, the key thing here is always thinking what the bearing is from. So if it's from A, that's another way of saying it starts from A. And so we start from A, facing north, and go clockwise, turning until we eventually end up facing B. And that's the bearing we want to find. And so for this one, part A, angles on a straight line, this portion of it's 180, so it's 180 plus an extra 40, it's a bearing of 220 degrees. Whereas for part B, one of my students who I was actually in the army mentioned this to me. If you switch the order of the letters, it's always going to be 180 degrees difference. Okay, so we know the answer based on what this person told me. I wish I remembered his name. He was a very good student. It's going to be 180 degrees difference to this. So 220 minus 180, it's going to be 40 as an angle. As a bearing, it's 040. It's called a back bearing. So doing it the longer way, which I would only do up until quite recently, we go 2A from B. So we look at B and draw a north line from B going up. So A from B, we start at B, go clockwise until we're facing A. And as you can see here, using the idea of Z angles, because this is 40, the angle with the vertical, this as well, should also be 40. But of course, just take a bit of care, because you talk about bearings, you can't put the bearing as 40 degrees. Bearings are, by definition, 3 digits, so the bearing would be 040. Question 2 is about a postman. Postmen are always underrepresented when it comes to questions, so it's good to see a postman here. Even less represented are postwomen, so maybe it should be post-person. Anyway, I digress. A postman walks 1 kilometre due east from a fixed point O to A, and then due north for 3 kilometres from A to B. So draw a diagram to represent the total journey from O to B. So it starts at O, so let's just pop in O. So first off, we're told that this postman walks 1 kilometre due east. So due east, never eat shredded wheat. East on a page looks to be to the right. And so east, 1 kilometre. So from O to A is 1 kilometre. And then at A, he goes due north, which is straight up on a page from A to B. And so we need to make a line which is roughly 3 times longer than the one we've just done. It doesn't particularly matter too much about the scale, as long as the diagram shows what's happening, more or less. So from A to B is like this. And so draw a diagram to show the total journey from 0 to B. So 0 to A to B looks something like that. For part B, we need to write down the position vector of B from the fixed point O. So the position vector of B is simply OB. So OB is from O to A, and then from A to B. So from O to A, we're going 1 to the right, 0 up or down. So that's going to be 1, 0. And then from A to B, we're not going left or right at all, so none to the right, but we are going 3 up. And so this is 1 and 3 kilometers. If like, we're going 1 along and 3 up. So what we do here is just pop in from 0 to B. We're going 1 to the right and 3 up. And so in kilometers it'd be this. This isn't the direct route. To find the direct route, we'd have to do the square root of 1 squared plus 3 squared. But that's all we need to do for question 2. For question 3, we have a binomial expansion question. So we need to find, in ascending powers of x, where the powers of x are growing, the first 3 terms in this expansion. So the good news is we don't need to do the whole thing, just the first 3 terms. So the general rule is the first term is the power of a bracket, choose 0. The first term, which is 3 to the power 6, which again is the same as the power it's being raised to. And the final thing is not going to feature at first, so this is going to be to the power 0. Now, like I mentioned before, the power of the second thing in the bracket will always match the number at the bottom of the n choose r function. Now, as we go along, this bottom number here will increase by 1 each time. So 0 add 1 becomes 6 choose 1. This number here, the power of 3, will reduce by 1. And the power of this minus 1/9 of x will increase by 1 each time, which will match, as ever, to this bottom number, like I said earlier. So that's a 1, that's a 1. So if we keep going, 6 choose 2, 3 to the 4, then minus 1/9 x squared. And again, as you can see, 2 here, 2 there. And again, the power sum of each term, 4 plus 2 is 6, 5 plus 1 is 6, 6 plus 0 is 6. So when you spot the pattern to this binomial expansion, it isn't actually too hard at all. So how do we actually work out these things on a calculator? I'll show you now. So get your classes ready, and what we're going to do is we're going to press the first number here, which is 6, so 6, then press shift and the division symbol, so 6, choose 0, multiplied by 3 to the power 6, and then anything to the power 0 is just 1, and as you'll see, 6 choose 0 is also going to be 1. So we're just going to be left with 3 to the power 6 here, which will be 729. The next one, 6 choose 1, so we can toggle back to make it easier to type in. So delete, press 1. Instead of to the power 6, we now want 3 to the power 5, so delete, press 5. And then we want minus 1/9 to the power 1. It's going to multiply by minus 1/9. We get minus 162. So rather than a plus, I guess it's a plus, it's actually minus 162. So minus 162x. Then this thing here, we've got 6 choose 2, So it's going to be 6, choose 2 on the calculator, so 6, choose 2, multiplied, let's give yourself more space, times 3 to the 4, and then minus 1 over 9 squared. So we're going to have to square this next. And what we've got here is positive 15. So we have positive 15 x squared. And of course the expansion goes on, but we're only asked for the first 3 terms, and so that'll suffice for our answer. Question 4, we have a trigonometric identity again. So we need to show that 1 over cos x plus 2 sin x tan x equals 5. And we need to show this can be written in a different form. 2 cos squared x plus 5 cos x minus 3 equals 0. So I'm going to show you what steps you can take to have this rearranged in the correct format. So first of all, what we're going to do is look at this and realise that tan x can actually be written in terms of sine and cos. So leave the 1 over cos x as it is, and say it's the same as 2 sin x, but then tan x, tan is the same as sine over cos. So we can say it's the same as sin x over cos x equals 5. So all I'm doing in this step is just replacing tan with sine over cos. So then, if we simplify, we have 1 over cos x plus 2 sine squared x, because 2 times sine is 2 sine squared, all over cos x equals 5. So now what we can do is multiply the whole thing through by cos x. So we get 1 plus 2 sine squared x equals 5 cos x. But if you notice, our target has no sine terms in, nor any sine squared terms in. So we need to remove this sine squared x. And at this point, it's worth remembering that sine squared x plus cos squared x will always equal 1. That's a powerful trig identity. So in other words, sine squared x is the same thing as 1 minus cos squared x. So this little snippet is well worth remembering in terms of replacing what sine squared x is. Sine squared x is, of course, 1 minus cos squared x. So in our next step, we can make this substitution. But sine squared is 1 minus cos squared x. This right hand side stays as it is. So let's expand this out. So 2 times 1 is 2. 2 multiplied by minus cos squared x is minus 2 cos squared x equals 5 cos x. So now if I add 2 cos squared x to both sides, I get 2 cos squared x on this side. Leave this 5 cos squared, so I leave the 5 cos x as it is. And finally, it's just 1 plus 2 is 3, so subtract 3 from both sides. We arrive at what we wanted to, and we prove the identity. So that's all for the warm-up. Let's move on and have a look at the main body of the lesson. So today we're going to be talking about modelling with vectors in particular. So, in mechanics in particular, vector quantities such as displacement, velocity and acceleration and force have both a magnitude and a direction. You can also refer to the magnitude of these vectors. So the magnitude of a vector is a scalar quantity. So it's just a number So 4, 5, 6, pi, whatever. So it has a size, but no direction as such. So speed is the magnitude of the velocity vector. So speed, if you're going 60 miles an hour on the motorway, it doesn't really matter as such what direction you're going. You'd be going 60 miles an hour if you're going from Leeds to York, in the same way as you're going from York to Leeds. The speed doesn't really take into account the direction you're going, it's just the size of the velocity. Whereas velocity takes into account the direction as well. In the same way, distance in a straight line between A and B is just the size of the displacement vector. So displacement takes into account the direction, distance is just the size of the displacement. When modelling with vectors in mechanics, it is common to use the unit vector j to represent north and the unit vector I to represent east. So this is a question for you now. Can you think of a situation where the velocity is changing but the speed remains constant? So just ponder that for a moment, pause the video if you need, and just think about it. It's not actually that obvious. Okay, well here's two examples that just popped into my head. So one example is driving on a motorway at a certain speed, let's say 70, whilst changing lanes. So if you change lanes, you change in direction, but you can maintain the speed of 70 miles per hour whilst doing so. So your velocity might be changing because you're changing lanes, you're changing direction, but your speed could stay at 70 miles per hour. So the speedometer, I think it's called the odometer, might maintain a constant reading of 70 despite the fact you're changing direction. Another one is planetary motion, for example the moon, or not the moon's a planet, it's a satellite, or the Earth. So the Earth is going at a more or less constant speed around the Sun, in the same way the moon goes around the Earth at a more or less constant speed. However, because its direction is always changing, its velocity is changing, despite the fact its speed is pretty much constant. So let's have a look at a worked example of this. So modelling with vectors. So calculate the speed and distance travelled by a particle moving in a straight line with velocity 8I minus 15j meters per second for half a minute. That's going to bug me, so I'm just going to try and remove that red bit. There we go. So half a minute means 30 seconds. So we need to remember now that speed, all we mean by speed is the magnitude of the velocity. So we need to work out the magnitude of this velocity vector. So the velocity vector here is 8I minus 15j. So working out the magnitude of this is 8 squared plus minus 15 squared, which comes out to be 17 exactly. So the speed is 17 meters per second. And the distance travelled is given by a formula. So distance travelled equals speed multiplied by the time of motion. So the speed is 17 because you worked out the speed from the magnitude of the velocity. And the time of motion, we're told that it's been travelling for half a minute. So the time of motion is 30 seconds. So it's been travelling at 17 meters per second for 30 seconds. The distance travelled will be therefore 17 multiplied by 30, which will come out to be 510 meters. So that's the distance travelled, and the speed is 17 meters per second. Question 2. A particle P is accelerating at a constant rate, and we're told at a time t equals 0, P has a velocity u, which is 2I plus j, and 4 seconds later, P is moving with velocity v, where v is 7I minus 3j meters per second. So the acceleration vector A of the particle is given by this formula here. Essentially, acceleration is a change in velocity divided by the time taken to make that change. So we need to find the magnitude of the acceleration. So what we need to do first is to actually work out what A is. So A is V, which is 7i minus 3j. So I'm going to put this in column vector form. This is just my own preference. Minus U, which is 2i plus 1j, divided by 4. So when you divide by 4, it's the same as multiplying by a quarter. So it's a quarter of 7 minus 3 minus 2, 1. So we have a quarter. 7 minus 2 is 5. Minus 3 minus another 1 is minus 4. Now, when we're multiplying a vector by a scalar, we can multiply the scalar by each of the I and j components. And so this is the same as a quarter multiplied by 5, which is 5 quarters. And then a quarter multiplied by minus 4, which is minus 1. So in other words, we've worked out what A is. So vector A is this, which, if you prefer, in I and j form, is 5 quarters I minus j. We need to find the magnitude of this acceleration, though. So we worked out the acceleration, A, but to work out the magnitude of the acceleration, we need to find the size of it, which is the magnitude. So what we do is we square root the sum of both I and j components squared. So we sum 5 quarters squared plus minus 1j minus 1 squared. And what that gives us is going to be the magnitude of A. So if we get our calculator ready, so we're going to do the square root of 5 quarters squared plus minus 1 squared, which will just turn out to be 1, but you can type it in exactly as it is on the calculator if you prefer. So we get root 41 over 4, but in terms of an actual decimal answer, we get 1.60 to 3 sig figs. So acceleration is 1.60 meters per second squared, given to 3 significant figs. Finally, question 3. We have two forces F1 and F2 acting on a particle P. The resultant acts in a direction parallel to vector I minus j. So we need to show that P plus Q equals 3. What we need to do here is to work out the resultant force. So the resultant is the sum of F1 plus F2. So F1 is 1i minus 4j, and F2 is pi plus qj. So adding the I components, we see that this is equal to 1 plus p, and the j components, we see this is minus 4 plus q. And we're told that this is acting parallel to the vector I minus j. We need to now remember that if a vector acts in the parallel direction to another vector, that we can write this as a multiple of this other vector. So because this is parallel, the resultant force is parallel to I minus j, we can say that this resultant force is some multiple, let's call it gamma, of I minus j. So 1i minus 1j. And so now if we just look at the I components, 1 plus p equals lambda times by 1, which is just lambda. And the j components, minus 4 plus q equals lambda multiplied by minus 1, which is minus lambda. So if we now add these two simultaneous equations together, we get 1 plus minus 4, which is minus 3, p plus q, which is obviously just p plus q, equals gamma plus lambda plus minus lambda, which is 0. If we now add 3 to both sides, we see that p plus q must therefore equal 3. The question, remember, wasn't to solve what p and q was, so just read it carefully. We just needed to show this, and we have done here. So now we're done. So that concludes the worked examples. It's now over to you, ladies and gents, to try some of these yourselves. So if you could please turn to page 250, 11F on your Year 12 book. Try questions 3A and B, and then 4, 5, 6, 7, 8. Self-assess, use the back of the book to help you. If you're not sure, ask a peer, somebody sat next to you, and if you're not sure at all, what you need to do is just ask me via email, the channel, or come and find me in college. You know where I live, you know where I am. Not actually where I live, but you know where I am in college, is what I mean to say. Anyway, happy hunting, try hard on these questions, and please do keep in touch. Please subscribe to the channel, and I hope to see you all soon. Thanks for listening and getting to the end of the video. I hope to see you all very soon. Bye.